Okay, here's a typical first example involving u-substitution. So I've broken it down into 3 steps here, and this serves as a pretty good template. It's one I use pretty much all the time. First thing you want to do is look at the function and see if you can identify 2 functions where one of them is the derivative of the other. So it looks like here 2x is the derivative of x squared minus 9. So I'm going to let u equal x squared minus 9. So once I've identified the substitution, now I'm going to symbolically differentiate both sides. In other words, take the differential. So du is equal to 2x dx. And now I'm going to solve for dx. And so du over 2x is now equal to dx. So now I've got everything that I need in order to make this substitution. I know what u is. Right, and then I know what dx is going to be. So now the next thing I'm going to do is make the substitution and reduce. So the given integral or antiderivative 2x square root x squared minus 9. I know x squared minus 9 is u. I'll just recopy the g prime of x part. So I've got the antiderivative 2x square root u. What is dx? It's du over 2x, so that's what I'll write here. And so now the 2x's will cancel, and I'm just left with the antiderivative of the square root of u. So we can definitely find the antiderivative of this thing because this is a power function. So now I'm going to integrate. So how do I do that? Well, I'll write square root u as u to the 1/2, add 1 to the power and divide by the new power. So u to the 3/2 over 3/2. Flip the bottom and multiply by the top. 2/3 u to the 3/2 plus c. And now I got to remember to substitute what u is in terms of x. So now what is this thing? So it's 2/3. And now u is x squared minus 9. So x squared minus 9 to the 3/2 plus c. So 2/3 quantity x squared minus 9 to the 3/2 plus c. So this would be a good final answer for this exercise. Okay, here's an example very similar to the last one that we just did. So it's like a thing times a radical. And if you look at the more complicated part of this expression, the 2x squared minus 8x plus 1, if you differentiate this thing, you get 4x minus 8. So now that doesn't exactly match what's on the outside of the radical, so I won't be able to cancel everything, but I'll be able to cancel most of it. And the only thing that'll be left after the cancellation is a constant, and those are easy to deal with. So here's what I'm going to do. I'm going to let u equal 2x squared minus 8x plus 1. That means that du is equal to 4x minus 8 dx. And so now that tells me that, write it over here, that du over 4 times, let's write this as 4 times x minus 2 is equal to dx. And so now I've got my u substitution, and I know what dx is, so let's go ahead and make the substitution. So let me call this the integral I, so I don't have to rewrite it. So now this means that I is equal to the antiderivative, right? Copy down the g prime of x part, so x minus 2, and then the square root of u, right? That's what u is equal to, and then dx is du over 4 times x minus 2. And so now the x minus 2's will cancel, and I can take the 1/4 now and write it on the outside of the antiderivative. So now this tells me that I is really equal to the antiderivative, 1/4, the antiderivative of, let's say, u to the 1/2 du. So you know what to do from here, right? Add 1 to the power, divide by the new power. This is exactly the same reduction that we got in the previous example. So I'll leave the remainder of the solution as an exercise. Okay, here's another one. So again, ask yourself the same question. Try to find two functions. One of them looks like the derivative of the other. It looks like if I differentiate the thing in the denominator, I get 6x squared plus 6x. That's not going to exactly cancel the thing in the numerator. It cancels almost everything. So we'll just be left with a constant, but that's fine. So now I'm going to let u equal 2x cubed plus 3x squared minus 7. And so that means that du is equal to 6x squared plus 6x dx. And so now the next thing I want to do is solve for dx. So let me go ahead and call this 6 times x squared plus x. Whoops. And so now I've got everything that I need in order to make the substitution. So now this tells me that the antiderivative I now is equal to, let's say, x squared plus x. I've got a u in the denominator. And then what is dx? Well, it's du over 6 times x squared plus x. So now the x squares plus x will cancel, and I'm left with a 1/6, so I can write that out front. So now this tells me that I is equal to 1/6, the antiderivative 1 over u du. So now we've reduced this complicated expression to this much simpler antiderivative. We know what the antiderivative of 1 over u is. It's natural log of the absolute value. So this is 1 over 6 natural log absolute value of u plus c. And so now I just need to remember to substitute u with what it really is. So that's this thing. So I guess right here. So 1/6 natural log, and then 2x cubed plus 3x squared minus 7 plus c. So that would be a good final answer for this example. Okay, here's one involving a generalized exponential, same program. Try to find two functions where one is the derivative of the other. So it looks like the derivative of the thing and the exponent, the more complicated expression, is 6x. That almost cancels with the x out front here. We'll just be left with a 1/6 again. So as usual, let me let u equal 3x squared minus 7. That means that du is equal to 6x dx. Now I'm going to solve for dx. That says that du over 6x is equal to dx. And so now I can make a substitution and reduce. So this is the integral e to the u. Dx is du over 6x. The x's will cancel. I can write the 1/6 out front. This is now 1/6, the antiderivative e to the u du. We certainly know what the antiderivative of e to the u is. So this is 1/6 e to the u plus c. And now, of course, I want to write my answer in terms of x, and so I just recopy what u is. So this is 1/6 e to the 3x squared minus 7 plus c. So this would be a good final answer for this example. Okay, here's one that almost looks like the basic fourth root of x function. The only thing is it's got a linear shift, so it's not composed with any higher order polynomials. It's just a basic linear function under the radical. So here, there's not two functions involved. Really, if I just look at the 3x minus 5, when I differentiate it, I'll get a 3. That's already a constant, so those things really aren't a problem. So this thing, in order to anti-differentiate, I'm going to let u equal 3x minus 5. Run the usual differential program. So du is equal to 3 dx, and that means that du over 3 is equal to dx. So now I can rewrite this thing. The antiderivative of u to the 1/4 power, and then dx is really du over 3. So now I can just write the 1/3 out front. This is 1/3 antiderivative u to the 1/4 du. Of course, to anti-differentiate this thing, I'm going to add 1 to the power and divide by the new power. So I get u to the 5 over 4 over 5 over 4 plus c. And now I can flip the bottom and multiply by the top. So 4 over 15. And then u to the 5 over 4, that's 3x minus 5 to the 5 over 4. Plus c. I skipped an arithmetic step or two in there. That's okay though, just make sure you're good on how I got from here to here. Anyway, this would be a good final answer for this antiderivative. Okay, here's another one involving a basic trig function. So you can see the two functions x to the 4th plus 3 and 2 times x cubed. It looks like this thing is almost the derivative of this thing, so I'm going to call u equal to x to the 4th plus 3, and then we'll run the usual differential program. So u equals x to the 4th plus 3, du is equal to 4x cubed dx, and so that says that du over 4x cubed is equal to dx. And so now I can make the substitution 2x cubed sine of u, dx is du over 4x cubed, so the x cubes will cancel, and now 2 over 4 will reduce to 1/2, so I can write that in front of the antiderivative. So here's a really good reduction. We know how to find the antiderivative of sine of u. That's negative cosine of u. So negative 1/2 cosine of u plus c, and then substitute u back again. So negative 1/2 cosine of x to the 4th plus 3 plus c. So this would be a good final answer for this thing.